We know that in the mice you rarely see that many CD8 cells in an organ unless there's a virus infection going on at any rate. What else we can do with these samples, and I just wanted to show this briefly, we can find autoreactive CD8 cells with specificity for islet antigens by direct staining with tetramers. The tetramers come from Bar Group in Leiden. These are A2 restricted tetramers. It's the same patient from the NPOD consortium. These particular cells are specific for IGRP. You can then, when you look over the whole pancreas, you can find specificities for GARD, IEPP, proinsulin, many for them IGRP, and then also many islets that have not any infiltration or signal in this given patient. So you find a lot of heterogeneity in terms of the autoreactivity you can find. So that's pretty much at this point how the situation presents itself in terms of viruses maybe creating a fertile field in the pancreas and resulting autoreactive cells entering the islets. Of course, there's still many things, as I indicated, on the way that need to be learned. We don't know really what causes the class 1 upregulation. We need to stain for interferon and for viral presence and see how that comes about. I think there are still many unanswered questions. I think the class 1 is important enough and curious enough that we need to resolve this, because it's not a normal finding. And if this is specific to diabetes patients and not normal controls, it will tell us something. Because class 1 systems, interferon systems, are usually tightly regulated. They also shut down relatively fast if the causative agent is removed. Could it be just to the autoreactivity or some innate immunity? I would think yes. And we just cannot exclude that at this point, because of course NK cells and CD8 cells make interferons, and that could lead to this upregulation of class 1 if they are constitutively activated and present in the islets. So, coming to the flip side of this whole situation, the issue that pathogens can prevent autoimmunity, and this finding, this is not a new hypothesis. People have referred to this as the hygiene hypothesis a long time ago, and it has been studied epidemiologically in many, many cohorts. It not only applies to type 1 diabetes, it applies to MS, it applies to also allergic diseases. And it's quite interesting. We had just a meeting in Berlin earlier this year where also Jean-François Bach, who was quite interested in this, was present. There is good epidemiological studies. For example, things that they call the sibling effect and the farming effect, in the sense that if you have young siblings, you have less asthma and allergic diseases. If you grow up on a farm, depending on whether they are large or small animals, you have less allergic diseases and so forth. And so there's some indications that there's value to this hygiene hypothesis. It's just not easy to study. There's also very, very good studies by a guy in Germany who does immigrant migration studies for people who, for example, immigrated to Germany, in this case from Turkey or other countries, and who retain their status of being less prone to asthma, allergic diseases, or autoimmunity for at least a year. Till then, something happens, which we don't know. They're blocked from the host country, and then the incidence of asthma and so forth goes up. So it's quite interesting and intriguing. It's easy to say it's all hygiene, but isolating the factors is not an easy endeavor. There can be many factors. And last but not least, it could be related to the gut microbiome. It could be related to infections. It could be related to complex interaction between lifestyle, food intake, the resulting gut microbiome, which is many times shared within families, and which can change over time if you're exposed to a different nutritional environment. Studying this is not easy, and mapping it to a single culprit or pathogen is not easy either. But it's intriguing. It's also intriguing to think that the immune system evolved as host defense, and that if we have less infections now in childhood, the immune system gets trained less, and because it gets trained less, it gets bored and starts doing things it's not supposed to do, which is causing allergic lung disease or autoimmunity and this and that, because the repertoire systemically gets changed, because it's not tuned by diphtheria, pertussis, and all these type of childhood diseases. Of course, now also difficult to study, because when we reduce the childhood diseases, many other things changed in terms of lifestyle. So So you cannot just say, okay, we have less childhood diseases, it's easy, that's got to be the culprit. With all the reduction in childhood diseases came changes of lifestyle and water cleanliness that have many other factors, so it's not easy to study. What you can study, though, to make a long story short, is what virus infections do mechanistically in animal models when they prevent diabetes. And it was a big surprise to us that it's a rather common event, one should say. Very interesting. So when we study this in our two diabetes models, the virus-induced model and the NOD model, you can see here is for enterovirus infections. It's very similar for LCMV, that in many scenarios you get a reduction of diabetes incidence that's quite profound. Whereas acceleration here in this case is only at certain times seen, and it's relatively mild. It's only seen in this model if you do it early, but in many cases you can reduce the incidence of diabetes. Now think about this. You have an enterovirus, Coxsackie B, infects the heart, infects the pancreas, so you're in the target organ. It makes a heck of an inflammation, all kinds of chemokines and things go up. And what you do, you prevent diabetes. It's rather counterintuitive. And we have done this obsessively in many mice. Stephen Tracy from the University of Oklahoma has done this with various Coxsackie B strains and has found the same thing, that the event of preventing diabetes is very common. Even more so, if you want to add to this story, we have made a Coxsackie B virus recombinant expressing the insulin B chain, an autoantigen. So now you infect with a virus that expresses an autoantigen and infects the pancreas, and what you get is prevention of diabetes. It's very, very common and very, very solid observation where we should not close our eyes from that, because it's probably a very common scenario when you undergo an infection, at least based on these animal models. So question now comes, how does this work? What mechanisms underlie this? And I will show you several mechanisms. One that intrigued us most is the effect of viruses on the polyclonal regulatory T cell compartment. So those of you who have been involved with immunology probably have followed the trend of regulatory T cells over the past 10 years. These are cells that many of them might be autoreactive, but you can also make them reactive to virus antigens, that recognize, upon recognition of the antigen, dampen immune processes. And they probably have many different phenotypical and functional signatures. Some of them make TGF-beta, some of them make IL-10, and some of them are FOXP3 positive, which might be a good indicator, at least in the mouse, and if it's properly demethylated, probably also in humans, of a good regulatory lymphocyte. Okay? So we looked at what happens to the regulatory cells and their cytokine production after you have virus prevention of diabetes, and this is how the experiment went. So you take, in this case, NOD mice. Normal incidence of diabetes is like this, 70 to 80% over time. You give them LCMV virus early on, same thing with Coxsackie B virus, you prevent diabetes. This observation is old. I think Michael Oldstone already had a paper in Science in 1980 about this whole business. Right? There was even an article in Scientific American that viruses now all protect from diabetes and we shouldn't worry about virus infection anymore. Like that. So that's an old observation. What is new now is you can take cells out of these virus-protected mice, in this case CD4, CD25 cells, 1 times 10 to the 6, and put them into a naive NOD mouse and host. You can also do this in the RIP LCMV model. And what you see is that these virally conditioned Tregs, as you might call them, prevent diabetes now very well. If you just take Tregs out of a NOD mouse, never prevents diabetes. You see this here. So the normal Treg compartment in the NOD is not potent enough, so you can transfer protection with 10 to the 6 Tregs. If you virally condition these NODs, you can transfer protection with this amount of Tregs. So something the virus has done to the Tregs to make them, as I call them, invigorated. So a virus invigoration of the Tregs. Now you can ask many questions. First of all, it's a bit counterintuitive. If you think about viruses in the context of regulatory cells, intuitively you would say, if you have a virus in the system, you would not want to activate or invigorate Tregs.